Welcome to this college algebra video about logarithmic functions. So what exactly is a logarithmic function? A logarithmic function is the inverse of an exponential function. In a previous lesson, we've talked about exponential functions, and in a lesson previous to that, we talked about inverse functions. Remember that an inverse function basically reverses the process of a normal function. It takes the outputs from the function and traces them back to the inputs that they came from. So specifically, the inverse of an exponential function will take numbers as input and find a power of the base as an output. Since different exponential functions have different bases, we could have 2 to the x, 4 to the x, 5 to the x, 10 to the x. The inverse function must specify the base of that exponential function. So a logarithmic function with base b looks like the expression on the left. We read that log base b of r is equal to p, and that is the reverse of the statement b to the p power equals r. So think of b as the base, p as the power, and r, I think of it as like the result. We can trace the result back to the power that it came from using a logarithmic function. Just as with an exponential function, b must be greater than 0, but not equal to 1. And since exponential functions only have positive outputs, the inputs for log functions must also be greater than 0. So the left we call logarithmic form of an expression, the right we call the exponential form of an expression. To put some specific numbers to an expression like this, here's a log expression. The log base 10 of 1,000 is equal to 3. And that is true because 10, the base, to the third power, p, is equal to 1,000. The idea is similar to ideas that you've seen in the past when you related addition and subtraction or multiplication and division. For instance, you can say 24 divided by 3 is equal to 8, and that is only true because 8 times 3 is equal to 24. So we have the expression written as division. We have the same relationship between these numbers written as multiplication. Well, in a log expression, we have a relationship between these three numbers. We have the same relationship between those same three numbers in this exponential expression. Let's use Desmos to explore the graph of a logarithmic function in comparison to the graph of an exponential function. In this illustration, f of x, the red graph, is an exponential function, 2 to the x. G of x, the blue graph, is a logarithmic function, specifically the log base 2 of x. That is the inverse of the exponential function 2 to the x. Notice that the graph is a reflection of the original graph over the line y equals x. The log graph takes points from the exponential graph and reverses their coordinates. So coordinates 0, 1 on the exponential graph are reflected as 1, 0 on the log graph. Coordinates 1, 2 on the exponential graph are reflected as 2, 1 on the logarithmic graph. And all the points on this logarithmic graph are simply points on the exponential graph with their coordinates reversed. We can also see this in this table of values, where on the exponential function, an input of 1 leads to an output of 2. But on the logarithmic function, an input of 2 leads to an output of 1. Similarly, on the exponential function, 3, 8 is an input-output pair. And on the logarithmic function, 8, 3 is an input-output pair. So in a way, we are using the logarithmic function to trace this 8 back to the power it came from in the exponential function, 3, and 2 traced back to 1. Now notice that at 0, our log function is undefined, and at -1, our log function is undefined. That's because 2 to the x can never equal 0. 2 to the x can never equal -1, or in fact, any negative number. Here's another feature of logarithmic graphs that I'd like to point out. Remember that exponential graphs always have horizontal asymptotes. In this case, the line y equals 0, or the x-axis. The logarithmic graph has a vertical asymptote. All logarithmic graphs have vertical asymptotes. In this case, it is the line x equals 0, or the y-axis. So we've seen that graphing log base b of x is just a reflection of the equation y equals b to the x over the line y equals x. The exponential graph passes through the point 0, 1, and so the log graph passes through the point 1, 0. We'll see that we can shift, stretch, reflect log graphs just like any other function. So let's explore a little bit of how to do that. Here are the same two functions we were looking at previously. This is 2 to the x and the log base 2 of x. And first, let's just see what happens if we change that base. As the base increases, notice that the exponential function gets steeper and steeper, but the log function gets less and less steep. As the value of the base approaches 1, graphs get closer and closer together, eventually crossing. The exponential graph gets less steep and the log graph gets steeper. At b equals 1, we simply have a straight line, which is not an exponential graph, and there is no inverse function for a horizontal line. We can continue to decrease our base and get closer and closer to 0. We see that the exponential function, the red graph, has turned into exponential decay, a decreasing function, and the log graph is still its reflection. This time the log graph is also a decreasing function. Before we start doing some calculations with logs, I want to give you a few basic facts about log functions. So here are some of them. Some of them may be more obvious than others. The first fact is that the log base b of 1 is equal to 0. This is true no matter what the base is, because any base to the 0 power is equal to 1. So the number 1 is always going to trace back to a power of 0. The second true fact is that the log base b of b is equal to 1. And again, this is true no matter what the base is. The only way to get an answer of b is to take b to the first power. The third fact that I want to mention is that b to the log base b of r is equal to r. This is because log base b of r is basically representing the power I would need to raise b to get an answer of r. So of course, if I raise b to that power, I should get r. We'll use this fact later on. And finally, the log base b of b to the p is equal to p. These two facts on the bottom are essentially ways that we are going to cancel out exponentials and logs when we are solving equations. So these two facts will become more and more important in future sections. So one of the first basic skills that you need to have when you're dealing with log functions and exponential functions is rewriting these functions from one form to another. So recall that we have the log form of an expression and we have the exponential form of an expression. These both represent a relationship between three numbers: the base, the power, and the result. So if we look at these three exponential expressions, we could also write them in a log form. Basically, we're trying to identify the base, the power, and the result. When written in a log form, we start out with log base. Well, the base of this expression is 4. Then we put the result, 64. We save the power for the very end. Log base 4 of 64 is equal to 3. It's another way of stating the relationship between these three numbers, the fact that 4 to the third power equals 64. Let's write this expression in a log form. First, we need to identify the base. That's usually the easiest part. The base is the big number here, so this is a log base 7. Next, we're going to put the result, the 49. So log base 7 of 49 equals the power 2. Finally, over here, we're going to write in log form, again, identify the base. The base is 3. So we say log base 3 of, the result is this fraction, 1 over 2187. And the power is negative 7. Log base b of r equals p. Now let's try the reverse. Let's take a log expression and try to write it as an exponential. Well, again, first thing to identify is the base. In this case, the base is 3. Our power is on the other side of the equal sign. 3 to the 5th power is equal to 243. Usually if you get these things in the wrong order, it's going to be pretty obvious. 3 to the 243rd power does not equal 5. In the next example, our base is 5, our power is also 5, and the result is 3,125. And in the last example, the base is 6, the power is negative 4, and the result is this fraction, 1 over 1,296. And this makes sense with our previous knowledge. We know that a negative power means that 6 to the 4th winds up in the denominator of this fraction. Another important skill is to be able to evaluate a log function. That is, figure out what the log base 3 of 81 is. At first, I'll solve these problems without a calculator so that we can get the concept, and then I'll show you how to solve them on a calculator. Let's start with log base 3 of 81. The idea here is that the base is 3, the power is unknown, and the result is 81. Well, we've solved exponential functions like this before by kind of a guess and check method. 3 to what power is equal to 81? And the answer is that the power needs to be 4. Remember that a log is basically identifying a power. Next, 2 is our base, our power is unknown, and we want the result to be 32. Well, you could try different powers of 2 until you find the right one. It turns out 2 to the 5th power is 32, so the log base 2 of 32 is 5. This one looks a little tougher. Log base 3 of the 4th root of 27. So our base is 3. We're looking for a power that will get us a result of 27 under a 4th root, or we could say 27 to the 1/4 power. I'm going to solve this problem by trying to get equal bases. 3 to some power is equal to, well, 27 could be written as 3 to the 3rd power, and 3 to the 3rd power to the 1/4 power. We can now use a property of powers to multiply 3 times 1/4, and now we can see that that unknown power would be 3/4. So the log base 3 of the 4th root of 27 is 3 over 4. So here's how we do these problems on a calculator. The log button on the front of the calculator is not a log base 2 or log base 3. It is a different log that we'll talk about in a little while. But to get a log base 3 or log base 2 of log of any base, you're going to hit the Math menu, work your way down the list until you get to log base. It is quite a ways down the list, but choose log base, and what will come up on the screen is a log expression waiting for you to fill in the base, in this case 3, and what we call the argument, in this case 81, and let's see what log base 3 of 81 is equal to. And the calculator tells us log base 3 of 81 is equal to 4. Let's try these others. We want to do log base, so math, and work your way down the list until you get to log base, quite a ways down the list, and then fill in the information for this particular log. In this case, log base 2 of 32. And the calculator agrees with our answer of 5. Finally, our third example, we hit the math button and work our way down to log base, fill in the base of 3, and now we have to do the 4th root of 27. Well, we can go back to the math button, And number 5 shows a root where we can fill in the index of that root, the 4th root of 27. Now, if you don't want to go to that trouble, you could also say 27 to the 1/4 power without having to go through the math menu. And again, this agrees with our answer. 0.75 is the same as the fraction 3/4. These next two examples are even simpler if we rewrite in an exponential form. We see that the base is 4, the power is 7, and the x that's missing is just the result of 4 to the 7th power. On a calculator, we can do 4 to the 7th and see that the result is 16,384. Moving on to the next example, we can see that our base is 8, our power is 1/3, and the x is the result of 8 to the 1/3. So just remember that a 1/3 power is the same as a cube root. Cube root of 8 is equal to 2. That tells us our x value is 2. Now let's talk about some different ways we can put logs together and take logs apart. And the rules I'm going to talk about here may not be exactly what you are expecting. For each of these rules, we're going to let b be the base of a logarithmic function, and basically these rules will apply no matter what the base is, and let m and n be variables that could represent positive numbers. The first rule says that the log base b of m times n is equal to the log base b of m plus the log base b of n. Let me illustrate this on a calculator. This won't exactly be a proof, but it may help convince you that these two expressions are the same. Now for each of these illustrations, I'll be using a window of x min -2, x max +10, y min -2, y max +3. So you can check these along with me if you'd like. So first, let's compare a couple of expressions that a lot of people would think would be the same. Log of parentheses 3 plus x, and most people would expect that it's going to equal the log of 3 plus the log of x, almost as though logarithm is distributing over the parentheses. But here's the graph of log of parentheses 3 plus x, and then we'll see in black the graph of log of 3 plus log of x, and we can see that these are very different graphs. So logarithm does not simply distribute through a parentheses, but now let's also add in the expression log of 3 times x, and we'll see this graph of log of 3x covering right over the graph of log of 3 plus log of x. Our next rule shows a relationship between division and subtraction. The log base b of m over n is equal to the log base b of m minus the log base b of n. For comparison, let's look at the log of 3 minus x versus the log of 3 minus the log of x. And if log could just distribute over parentheses, then these two expressions would be equivalent. But as we see, these two graphs are very different. This is the log of parentheses 3 minus x, and the black graph is the log of 3 minus the log of x. But if we now add in the log of 3 divided by x, we'll see that the red graph and the black graph are identical. So it's the log of 3 over x that's the same as the log of 3 minus the log of x. For our final rule of logs, I want to compare what happens when we take a log expression to a power versus what happens when we take the argument of the log to the power. So the difference between taking the whole log to the 5th power and just the x that we're taking the log of to the 5th power. Let's compare the graphs. Here's the graph of log of x entire thing raised to the fifth power, and the black is the graph of log of x to the fifth power. Clearly not the same. Now we'll look at the graph of something that seems very different. 5 times the log of x. And we'll see this red graph covers over the black graph perfectly. So our third rule is that the log base b of m to the k power is the same as multiplying the number k times the log base b of m. Now these three rules may seem a little bit confusing, a little hard to remember, but there is a definite logic to the way these things work. And the key is to remember that a log is the same thing as an exponent. And if you remember your rules for exponents, remember what happened when we multiplied. When we multiply two expressions with the same base, we add their exponents. When we divide two expressions with the same base, we subtract their exponents. So there's this natural relationship between multiplying and addition and dividing and subtraction. And when we're taking a power of a power, that's when we multiply exponents. So notice that k is an exponent and a log is an exponent. So it makes sense to multiply an exponent times an exponent. Let's work through a couple of examples that illustrate how we can use these properties to simplify log expressions. And simplifying a log expression is often going to be the first step in solving a log equation. So the first example starts log base b of m minus log base b of t plus log base b of c. It's important to remember that the base must be the same if we are going to use these properties of exponents. So the log base b of m minus the log base b of t could be written log base b of m over t. The subtraction is equivalent to division. Now we're still adding log base b of c. So this addition is now going to turn into multiplication. So altogether we could write the log base b of m times c divided by t. The second example has coefficients in front of each log. Those coefficients are first going to move up and take a place as an exponent. So an exponent of r, an exponent of j, an exponent of n. I'll write log base b of r to the third plus log base b of j to the 1/2 minus log base b of n to the 5th. And as a second step, I'll now combine these three expressions into one, changing addition into multiplication and subtraction into division. The expression becomes log base b of r to the third times j to the 1/2 divided by n to the 5th. These next examples show how we can cleverly use the properties of logs to go from just a couple of known logarithms to finding several unknown logarithms. Suppose it's given that log base 6 of 5 is 0.8982 and log base 6 of 7 is 1.0860. Now suppose we want to find the log base 6 of 35. Well, first notice that 35 is 5 times 7. Now use a property of logs to separate this into two separate logs. This will separate into log base 6 of 5 plus log base 6 of 7, or substituting 0.8982 plus 1.0860. If we just add these two numbers up, we find that log base 6 of 35 is 1.9842. Now let's try to find the log base 6 of 252. Well, 252 happens to be 7 times 36. So we can separate this into two separate logs. The log base 6 of 7 plus the log base 6 of 36. We were given the value for the log base 6 of 7, but we were not given the value for the log base 6 of 36. But if you just remember that 6 to the second power is 36, you'll know that the log base 6 of 36 is 2. So add 1.0860 plus 2, and we'll find the value for log base 6 of 252. For our third example, we'll split log base 6 of 30 into log base 6 of 5 times 6. Split that further using a property of logs into log base 6 of 5 plus log base 6 of 6. Log base 6 of 5 is given to us up above. Log base 6 of 6 is simply 1. Add these together, and we'll see that the log base 6 of 30 is 1.8982. Be careful as you are using the properties of logs that you don't use a property that is not true. Here's a list of a few non-rules that students often try to use by mistake. First, separating multiplication and continuing to use multiplication, or trying to take addition together and separate it into multiplication when you take it apart, or trying to distribute log over addition. These statements are not true. Do not simplify logs in this way. Here are a few that students sometimes mix up when we're talking about division. Don't change division into division. Don't change subtraction together into division when you take it apart. Don't distribute log over subtraction. These statements are all false. Don't try to use them. One good way that I've found to remember these rules is that when we are looking at expressions on the left side where the logarithm is put together, compared to log expressions on the right side where it's taken apart, the operation when it's taken apart should always be a weaker operation than when it's together. So multiplication can't turn into multiplication. Multiplication is not weaker than addition. In fact, there is no operation weaker than addition. So there's really no way to take addition apart into two separate logs. Division is not a weaker operation than subtraction. That clues me in that I should not take apart subtraction in this way. I hope you've learned something in this brief introduction to logarithmic functions. Now go out and try some practice problems, and we'll see you next time.